I'm Vinesha Peiris. I am a research fellow from the Curtin Centre for Optimisation and Decision Science. So today I am going to talk a little bit about function approximation by neural networks and rational functions. So I will kick things off with this quote by René Vidal, who is a great machine learning researcher during the previous years. So he once said, if you do things with 100% people who are all data scientists and machine learning people, they tend to think that all you need is a bigger network and more data. But I think we need to solve real problems, and the solution is not always more data and more annotations. So this is something I personally believe that mathematician could step in and help a little bit. So I will probably be able to give you some alternatives and some examples where you don't really need a bigger data set or bigger network to compute better approximations. So that is my target for today. Okay, so my talk is actually divided into 4 main sections. So in the first part, we will talk about how rational approximation works, especially in uniform norm. And then we will talk a little bit about neural networks. So I'm pretty sure that everyone is familiar with neural networks, but we will talk a little bit about the mathematics behind neural networks. And then we will have a look at a small comparison between approximations by rational functions and approximations by neural networks, and we will look at univariate and multivariate approximations. And then I will show you how we can actually improve neural network approximations using optimization and looking at this problem from the point of view of quasi-convexity. Okay, moving on to rational approximations in uniform norm. So these problems are usually called uniform approximation problems. Some people call them Chebyshev approximation problems, approximations in uniform norm, approximations in Chebyshev norm, and some people even call it min-max norm. So there are a lot of names, but they're all trying to do the same thing. So what we are doing here, we are trying to minimize the maximum absolute deviation between your original function and your approximation. The function f of t here is my original function. It is a univariate function. The variable is t. And then we have my approximation, which is psi of at. So t in psi of at is the same t as in f of t. And capital A here consists of the set of parameters that we can change. So we are looking for the set of parameters capital A that could give us as best as possible approximation in uniform sense. So we are trying to minimize the maximum absolute error between the original function and my approximation. So this approximation here, psi of at, in many cases, it is considered to be a polynomial, piecewise polynomial, trigonometric polynomial, or a rational function. So for this talk, we will be mostly looking at problems where this approximation psi of at is a rational function. Okay, now we will start off with the generalized rational uniform approximation. So in this case, my approximation is just a ratio of 2 functions. And in the generalized rational uniform approximation, we have a ratio of 2 linear functions. Now, capital A and capital B here, they consist of the parameters coming from the numerator and the denominator. And then we have g of t and h of t, they consist of the basis functions. And these basis functions, they usually consist of functions of t and their known values, right? So A and B are subjected to optimization. And of course, we want the denominator to be positive. So so this rational approximation was very, very fashionable during the 50s and the 60s of the 20th century. And this ratio here was first actually called ratio of linear forms because you have two linear functions, one in the numerator, the other one in the denominator. But later on, they actually renamed this ratio as generalized rational approximation. So if you want to have a look at an example of generalized rational uniform approximation, the classical uniform approximation is the best place to start with. So here again we have a ratio of two functions, but in this case we have a ratio of two polynomials. So ai's and bj's, they are the coefficients of the polynomials and they are the parameters. N and m, they are the degrees of the polynomials in the numerator and the denominator. And for the basis functions, we have monomials. So they are the t to the power i's and t to the power j. So we just have monomials here. And of course, again, we want the denominator to be positive. And throughout this talk, if I say classical rational functions or classical rational approximation, then I'm referring to a ratio of two polynomials. If I say generalized rational function, then I'm talking about a ratio of two linear functions. Okay. Now, as I said, rational approximation was very, very fashionable during the 50s and the 60s of the 20th century. And there are a lot of classical algorithms that you can use, and most of them are actually based on linear programming techniques. So if you are interested, the paper by Lee and Roberts is actually probably the best place to start with. They have a very comprehensive examples, comprehensive descriptions about all these algorithms. And in recent years, there were two modern enhancements. So one was the AAA method. It was developed in 2018. It is very fast, but it has a lot of limitations as well. So for an example, if you want to use AAA method, you cannot use two different degrees for the numerator and the denominator. You need to stick with the same degree. And at the same time, as far as I am aware, it has not been extended to multivariate approximation, so you can only deal with univariate approximations. But on the other hand, we have bisection method, and this actually uses the quasi-convexity property of the objective function. And you can use two different degrees for the numerator and the denominator, polynomials, or even linear forms, so even generalized rational functions. And you can extend this method to multivariate functions as well. Okay, now if you're wondering how powerful rational approximation is, then here is an example for you. So the blue line here is my original function. So square root of the absolute value of x minus 0.25. So it's a nonlinear, non-Lipschitz function, very, very hard to approximate. And we have this very sharp, very abrupt change at 0.25, right? So this pink line here is a polynomial approximation of degree 8. So we have 9 parameters in total. So the parameters are the coefficients of your polynomial of degree 8. And this black line is the rational type 4, which means you have a degree 4 polynomial in the numerator, degree 4 polynomial in the denominator. But usually we fix the constant coefficient of the denominator at 1 just to make sure that the denominator doesn't go to 0. So again, we only have 9 parameters in total. So for this polynomial approximation and rational approximation, we have the same number of parameters, but as you can see, rational approximation is very, very close to the original function, and it is computing a much better approximation compared to the polynomial approximation. So rational functions are actually very flexible, and it can produce much accurate results in terms of approximation. Okay. Now, moving on to neural networks. So I'm pretty sure all of you are at least heard about neural networks, but we will be going through a bit of basics and a bit of mathematics behind neural networks. So neural networks are a layered structure. So you start with your input layer, and at the end, you will have your output layer. And in between your input layer and your output layer, you can have as many as hidden layers you want. So usually the colored circles here, they are either called nodes or neurons, doesn't matter what you call them. I will be mostly using the word nodes. So the number of nodes in your input layer and the output layer depends on the type of problem that you want to solve. But the number of hidden units or hidden nodes in your hidden layer is it depends on the user. So you can select the number of nodes that you want to use inside your hidden layers. Now these connections between nodes, so these arrows, they are called weights, and the objective here is to optimize your weights. So that's how a neural network usually works. So if you have a look at the mathematics behind a neural network, so in this case, assume that you are going from inputs to outputs directly. So you have no hidden layers at all. So you have a very simple network where you directly go from inputs to outputs. So in that case, your output will be this pi function, pi of wx, right? And it can be actually written as a composition between sigma and this affine transformation here. Now these wj's and w0, so w's in total, they are called the weights and they are subjected to optimization. And this sigma here is called the activation function, and it is usually not subjected to optimization. It is there to actually introduce nonlinearity to your optimization problem or to your neural network. But in some cases, you can have learnable activation functions where you have a few parameters inside your activation function that can be learned when you are learning your weights or when you're optimizing your weights. Together with the weights, you can optimize some of the parameters of your activation function. Now, this is when you go directly from inputs to outputs, right? But if you have one or more hidden layers present, then your final output will actually become a repetition between compositions and affine transformations. So you take the composition between your activation function and transformation, and you keep repeating it for every layer that you have in your neural network. Okay, now how do we actually find these weights? How do we optimize the weights? So in order to do that, you have to compute your loss function, which is also called the error function. And when you minimize this error or the loss function, you will be able to optimize your weights of the network, right? So your weights are the parameters of your optimization problem. So least squares or mean squared errors is usually the most popular version of error that people have been using. But for this talk, we will be mostly dealing with loss function based on uniform norm, where we minimize the maximum absolute error between the original output and the output computed by the network. Okay, there are also connections between the Kolmogorov-Arnold theorem and neural networks. So if you are not familiar with the Kolmogorov-Arnold theorem, it was actually developed as probably as a solution or an answer to the very famous Hilbert's 13th problem. So it simply says that every continuous function f can be represented by using summations and compositions of one variable functions. So that's what the Kolmogorov-Arnold theorem simply says. And in 1987, H. Nielsen, he actually showed that Kolmogorov-Arnold representation theorem can be seen as a three-layer neural network. But the difference is, so in a neural network architecture, we would compute the affine transformation first. So we introduce the linearity first. And then we introduce the activation function. So we take the compositions, and that's where we introduce the nonlinearity. But in Kolmogorov-Arnold theorem, we will be actually introducing nonlinearity first, and then we introduce the linearity. So that's the only difference here. Okay, now we are going to have a look at univariate and multivariate approximations by rational functions and neural networks. So we now know we are dealing with rational functions in uniform norm, so rational approximation in uniform norm, and we are now going to construct a few neural networks, but they are very, very simple, and the loss function is actually based on uniform approximation. Now, but before we talk about these experiments, let's have a look at rational neural networks. So rational neural networks is, so for an example, if you take a neural network as very simple neural network, and if you take rational functions, and if they have a baby together, then rational neural networks is the name of that baby actually. So this was introduced in 2020 by Boole, Nakatsukasa, and Townsend. So they introduced rational neural networks. So as the name suggests, they are talking about neural networks where your activation function is a rational function. So instead of having a standard ReLU activation function, and ReLU is just the maximum between 0 and any given input, so you replace your very standard ReLU activation function by a rational function, but not just any rational function, a rational function where the coefficients are learnable, which means, so here AJs and BKs, they are the parameters, right? And these parameters are actually learnable while you are learning the weights of your network. And xj's and xk's, they are monomials, so x to the power j's and x to the power k's. So we simply have two polynomials here, one in the numerator, the other one in the denominator. So why is this important? Because AJ and BKs can be optimized. We don't have to fix them. And in this paper by Boole, Nakatsukasa, and Townsend, they also theoretically show that rational neural networks actually outperform ReLU networks in some settings. And they have a lot of applications, a lot of examples, and they have included applications to partial differential equations as well, which we will have a look at in a minute. Okay, now this paper actually led us to think about a question. So the question is, if you take a neural network and if you use rational functions as your activation function, then your neural network or the output of your neural network will actually be a rational function itself. So this actually led us to think a little bit more about this, and we were just really curious to see how this neural network with rational activation compares to the classical approaches of rational approximations, because ultimately you are just doing approximations and you are dealing with rational functions. So we wanted to work on a set of experiments where we simply compare the classical rational approximation techniques with neural network approximation techniques. Okay, so again, we are trying to compare rational function approximation and neural networks, but because for the rational approximation, we are dealing with uniform approximation norm, so we decided to use uniform norm-based loss function for the neural networks just for the purpose of comparison. And while we are doing this, we are actually going to introduce a new training scheme for the rational neural networks, which is called the split training approach. I will talk about it in a minute. So we do have a few different types of neural networks. So first neural network is just a standard neural network, and the activation function is a ReLU function. And then we take another neural network, and in this neural network, the activation function is a rational function. And the coefficient of your rational function or the rational activation function are actually learned together with the network weight. So they are learnable parameters, they are optimized while you're optimizing the weights of your network. And then we have another network. And in this network, again, we have a rational activation function, but we use a different three-step alternating, or we sometimes call it split method. So what happens here? So you have three layers: input layer, hidden layer, and your output layer. So we have two sets of weights, right? One that goes from inputs to your hidden layer, and the other set that goes from hidden layer to your output layer. And we also have the coefficients of your rational activation function. They are also a set of parameters of your optimization problem. So in the first step, what we do, we fix the coefficients of my rational activation function, and we also fix the weights that goes from a hidden layer to the output layer. So those two sets are fixed, and we just optimize the um, weights that go from inputs to the hidden layer. So that's my first step. And once they're optimized, I go to the second step. And in the second step, I fix all of my weights, and then I just optimize the coefficients of my rational activation function. So that's the second step. And in the third step, I fix my weights that go from inputs to the hidden layer, and also the coefficients of my rational activation function. So they are fixed, and I optimize the last set of weights which go from hidden units to, or the hidden layer to the output layer. So that's the three steps that I am going to follow. And then all these neural networks are compared with the direct rational approximation from inputs to outputs. So we don't have any hidden layers or anything at all. We just use rational approximation directly to approximate the output of the data set. And for this, we are actually going to use differential correction method. This is again another powerful method based on linear programming techniques. Okay, so let's have a look at experimental structure. So every neural network is a three-layer network. So we have a input layer, just one hidden layer, and the output layer. And hidden layer contains 10 neurons, and the loss function is based on the uniform norm loss. Now here, the optimizer, because we were actually using TensorFlow and we didn't want to customize our optimization techniques, so we use ADAMAX, which is actually a variant of ADAM-based ADAM ADA method based on the uniform norm. So we were using ADAMAX as the optimizer to optimize the weights and the other variables of the neural network. Now, let me show you the function that I'm going to approximate. So this is a univariate function. This is a non-smooth, non-Lipschitz function. You saw this function earlier in one of the slides where we talk about the approximation power of rational functions. So this function has an abrupt change at 0.25, very, very hard to approximate, right? So, now, here is a comparison between two neural network approximations. The one on your left is the uniform approximation loss with ReLU activation. And on your right, we have rational activation with usual training, where we optimize all the parameters of the network in one go. So we call it usual training. So as you can see, rational activation is a bit more flexible and it's trying to find a better approximation compared to the ReLU activation. But if you try to compare the usual training with the split training method, where we do the optimization in 3 steps, there's not much of a difference. And split training looks like it's not that flexible as usual training, right? But if I try to now show you the difference between rational activation neural network, where you use usual training, and differential correction method, where you directly approximate your function, I don't think I need to explain anything here. Rational approximation, where you use differential correction, computes a much, much better approximation compared to the neural network approximations here. Okay, so if you are wondering the degree of this rational function that we used in rational approximation, where we utilized differential correction, the degree was degree 21 and 20. So 21 in the numerator, 20 in the denominator. That was because when you have a neural network with a rational activation function defined on your hidden layer, and the people who first introduced rational neural networks, they actually used degree 3 and degree 4, so numerator 3, denominator 4 for the rational activation function. So we were trying to stick with that same degrees. And when you have those degrees, the output function will actually look like a rational function whose degree of the numerator is 21 and the degree of the denominator is 20. So we were trying to use the same degrees for our approximations when we do direct rational approximations. So again, the degree for the differential correction method were 21 and 20. So if you want to have a look at the loss function values and computational time, so here is a small comparison. So all three neural networks, they do actually compute loss function values that are very, very close to each other. And the runtime is not too far away from each other as well. But neural network with rational activation function where you have usual training is working at least a little better than ReLU or split training. But if you take differential correction method, loss function value is much, much, much smaller, and it computes this approximation in a split second. Okay. Now, let's move on to multivariate domains. So we discussed univariate functions and approximations in univariate functions. Now we are going to have a look at multivariate functions. So just one function. So we are going to approximate a solution to a KdV equation. And we are now going to use the bisection method, which is a method that developed by using quasi-convexity property of the objective function of the generalized rational approximation problem. So we will discuss this bisection method later today. So we are going to use multivariate bisection method in this case. So we have two variables, xi and ti. And UIs are the observational data, and the size of this observational data is 512 times 201. So it's a huge data set. Okay, so this is what the original data set looks like. So the picture on your left is the 3D view of the original data set. The left picture on your right is the 2D view of your original data set. So if you remember the paper where people introduced rational neural networks, they actually use the same data set to compute approximations. And in their case, they actually used 4 different types of neural networks with 4 different types of activation functions. So they have ReLU, sinusoidal, rational, and polynomial activation functions. And as you can see, the validation loss is actually going down much faster when you use rational activation. Now, in this case, they actually used mean squared error. So we cannot, even if we try to compare this with direct rational approximations, we cannot do it because we are dealing with 2 different norms. But just out of curiosity, again, we wanted to see how well bisection method can work and rational approximation work in general for this type of data sets. So these are the pictures I actually got. So yes, the color scheme is a bit different. That's because we were using MATLAB to compute these approximations by using bisection method. But when you have degree 20 and 20, for your rational approximation, you do actually get much better approximations, and they are very, very similar to the original data set that you saw before, right? Okay, now the rational neural networks that the authors Boole, Nakatsuka, and Townsend used, they actually used 4-layer networks, and in each layer they had 50 nodes. So in total they had 8,035 parameters in total. But for rational approximation, we only had about 400 parameters. So it is a very, very less number of parameters that we had in our optimization problems. But at the same time, as I said, we were using MATLAB, and when we feed the full data set into the MATLAB code, it actually crashed. It didn't like the amount of data that we were feeding. So we had to reduce the data set a little bit. So in order to reduce it, what we did, we actually took the pairs of every 10th point of the domain along each of the two dimensions in order to reduce the problem a little bit. And even with this reduced number of data points, even with this small number of parameters, we still get much better approximation. So again, going back to the very first code that I quoted, even with small number of parameters, even with small number of data sets, you can actually use direct rational approximation, so alternative techniques to get the same or better approximation results. Okay, now how can we actually improve neural network approximations? How can we somehow use optimization to improve neural network approximation techniques? So this is just our way of improving neural networks where your loss function is computed by using uniform norm Bayes loss. Okay, so why do we actually need this? That's mostly because standard optimizers like Adamax they're not very well suited for uniform norm Bayes loss functions. So we definitely need an alternative. So what we want to do, we want to look at this optimization problem from the point of view of quasi-convexity. So if we can somehow show that if we carefully select the activation functions and carefully structure the problem, reformulate the problem a little bit, then we can actually use quasi-convex optimization techniques to tackle this problem. So one very well-known quasi-convex optimization technique is the bisection method developed for quasi-convex functions, which is exactly the same method that we use for generalized rational approximation problems. And by using this, we can get better performance, better classification accuracies if you are dealing with classification problems. Okay, now, if you're wondering what a quasi-convex function is, we say that a function f is quasi-convex if its sublevel sets are convex sets. So quasi-convex functions are actually a bigger class than convex functions. So let me show you an example or a picture. So assume that you have this function that is given in blue. And if this function is quasi-convex, then you need to find a horizontal line that crosses through this function, which is alpha, right? And then what I'm going to do, I'm going to find the intersections of my original blue function and this alpha horizontal line. And then what I'm going to do, I'm going to find the corresponding domain values, which is this red line here. So this the set of domain points in this red line, if that is convex, then we say that the blue function here is a quasi-convex function. And this figure was actually created by Julian Ubon from Deakin University. And then we have quasi-concave functions. We say that a function is quasi-convex if the negative function is we say that a function is quasi-concave if the negative function is quasi-convex. And we say that a function is quasi-linear if the function is both quasi-convex and quasi-concave at the same time. So why do we actually need all this? This is mostly to compute or create a simple network where we directly go from inputs to outputs. So if you go directly from inputs to outputs, again, this is what your output function looks like. So here, sigma is your activation function. And if you carefully select your activation function, so for an example, if it is a Lie-Leroy function or a rational function of degree 1, 1, then this output actually becomes a quasi-linear function, which means your objective function becomes a quasi-convex function, which means you can use quasi-convex optimization techniques to solve this problem. So we are solving a network problem by using quasi-convex optimization. And in the case where you have a leaky ReLU function for your activation function here, then this logs function particularly works well in the case where you have a very small training data set with underrepresented groups, but you have to make sure that most points are valid and accurate points. Okay. Now, what is this bisection method that we actually talk a lot about? So bisection method was developed for quasi-convex function. Yes, there are name conflicts, but this is called bisection method as well. And this method actually relies on solving a convex feasibility problem at the midpoint of the bisection interval. And according to the feasibility of your convex feasibility problem, you can decide if you want to update the upper or the lower bound. And in some cases, the convex feasibility problem can be reduced to solving linear programming problem, and it makes our lives much easier. So for an example, when you solve the generalized rational uniform approximation problem, your convex feasibility problem is actually reduced to solving a linear programming problem. So very easy to solve, very easy to manage. Everything can be easily implemented in MATLAB or Python as well. Okay, so how does this actually work? So what you can do, you can take your original approximation function, so original loss function of your network, and then take your objective function and replace it by Z. And once you replace it by Z, it gives you these two constraint functions, right? And this reformulation is called problem 1. So the bisection method depends on the solution of your problem 1. So what happens in bisection algorithm? So you specify your upper and lower bounds first, right? And then what you do, you fix it at the midpoint of your bisection interval. And then what you have to do, you have to check if your problem 1, so this problem here, has a feasible solution. If this problem has a feasible solution, then you can update your upper bound. If not, you can update your lower bound. And you have to keep refining this interval until the gap between the lower and upper bounds become very small. So this feasibility problem usually becomes a linear programming problem in many cases. Even when you have a network with a lot of weights, a lot of parameters, this is still reduced to solving a linear programming problem. Okay, now here is an example. So we take a data set called hand outlines data set, and this data set only has 2 classes, and the training set has 1000 recordings, and the test set has 370 recordings. So in this case, what we want to do, we want to artificially create a smaller training data set because our network is using uniform norm-based loss function, and we wanted to create a scenario artificially where we have a smaller number of training data points in the training data set, and we are also artificially creating an underrepresented group. So what we do, we actually randomly select just 2 points from class 1 and 18 points from class 2 for my training data set. So now just 20 points in the training data set, but I still have 370 recordings in the test set. So compared to the test set, training set is now much smaller. And in this case, we actually trying to classify the points into these 2 different classes, class 1 and class 2, and we check the test set classification accuracy. So we compare mean squared errors and uniform norm. So the same network, we go directly from inputs to outputs, but 2 different loss functions. And as you can see, uniform norm is actually doing a better job compared to the mean squared errors in this case, right? So if you have a underrepresented group, if you have a smaller number of data points in your data set, you could still use alternative techniques, not just a mean squared error, some alternative techniques to get better classification accuracy results. Okay, and then what we do, we actually create some more, like a lot of experiments where we have small training data sets. So let's have a look at the figure on your left. So figure A. So in the x-axis, we have the accuracy of the uniform norm-based loss function, and in the y-axis, we have the accuracy of the mean squared loss function. And this blue line here in the middle, that's my reference line where x is equals to y. So as you can see, there's just two data sets, two lead ECG, Sony AIBO robot, and toe segmentation swan. So these three data sets are the only data sets that performed higher classification accuracy when we have uniform approximation based loss function. Now, again, what we want to check, we want to artificially try and reduce the number of data points in the training set. So the figure on your right, so that's figure B. As you can see, we only randomly generate training sets of 10 points. So we only select randomly 10 points, and that 10 points will actually be my training set now. And we perform the same experiments, but with the smaller number of training data points in the data sets. And as you can see now, almost all the data points except the earthquakes data set. So all the other data sets are actually now shifted to the lower half plane of the reference line. And this indicates higher classification accuracy computed by the uniform norm-based loss function compared to the accuracy of the mean squared loss function. So again, if you have a smaller training data set or if you have underrepresented groups, then there are alternative ways to improve the classification accuracy. Okay, now let me summarize everything. So we looked at how we can compare rational approximations in uniform norm with standard neural network methods. And rational approximations often match or outperform neural networks, even if you have a smaller number of parameters. And if you take a simple neural network, I wouldn't call it a neural network, a simple network where you go directly from inputs to outputs. And if you change your loss function or the error function to uniform norm-based loss function, and then you can carefully select your activation functions so that the problem becomes a quasi-convex problem. In that case, you can use any quasi-convex optimization techniques to solve the problem, but the most efficient is to use bisection method. And this technique actually works very well when your training data set is either limited in size or if you have underrepresented groups in your data set. And all of this work was actually done in collaboration with Nadia Sukorukova from Swinburne University, Julian Ugon and Rinia Diaz-Milan from Deakin University, and Vera Roschina from UNSW. Thank you very much for listening.